Welcome to the Data Hall YouTube channel. In this video, we are going to talk about the Fama and French three-factor model. So specifically, we would discuss the CAPM and the difference between CAPM and the Fama and French model. And then we are going to look into the basic idea of portfolio construction. We would discuss what is univariate portfolio sorting, the bivariate independent sorting, and the bivariate dependent portfolio sorting. Then we are going to discuss the breaking points or the cutoff points that are used to divide portfolios or stocks into different portfolios. We are also going to discuss the value weighted and equal weighted portfolios. Once you have the basic idea of portfolio construction, then we are going to look into how Fama and French constructs their SMB and HML factors. Lastly, we are going to discuss our code, the Stata R and the Python code that we have designed to replicate the Fama and French three-factor model. And later on, we would also discuss the five-factor model, the momentum model, and the other asset pricing models. We would also show that the factors that our code produces, the SMB and HML factor, they are quite similar to the one that are produced by the Fama and French's study. So let's get started. Let's discuss the CAPM, the difference between the CAPM and the FF model. So we have this CAPM model where we have expected stock return. And what it says is that the expected stock return is equal to the risk-free rate plus the systematic risk of the stock. And this RM minus RF is what we call the market risk factor. Now, this CAPM model is what we call a single factor model. Then we have different multi-factor model. One of the multi-factor model is the Fama and French three-factor model, where the expected return, the expected stock return is equal to, is dependent on three factors. In CAPM, we just have one factor, and that is market factor. In Fama and French three-factor model, we have three factors. First one is the market factor, which is the same one that we had in the CAPM. Then we have the size factor, and then we have the value factor. Now this beta 1 represents the sensitivity of a stock to this market factor. Then this beta 2 represents the sensitivity of a stock to size factor. And lastly, beta 3 represents the sensitivity of a stock to the value factor. So let's discuss portfolio analysis. What portfolio analysis is. Now, portfolio analysis is a non-parametric analysis technique that is used to study the impact of certain variables, certain independent variables, certain factors on the future stock returns, right? Now, what we do in portfolio analysis is that we take a variable of interest, an independent variable that we want to study, and we make portfolios on the basis of that variable. Once we make the portfolios, we calculate the portfolio returns, and we would like to see how the portfolio returns are changing once we move from one portfolio to another portfolio. So what is the pattern within these portfolio returns? Whether that is increasing with the increase in that specific independent variable, it remains same, or whether it is decreasing. So that pattern would tell us something about that impact of this specific independent variable on the stock return. Now, the idea of using this non-parametric technique is that its advantage is that it does not have any assumption related to data distribution or functional form or relationship between the independent and the dependent variables. So for example, if you want to use regression, then we would have to test certain assumptions, the heteroscedasticity assumption, the multicollinearity assumption, etc., etc. But with the non-parametric techniques such as portfolio analysis, we do not have to worry about these assumptions. The downside of this portfolio analysis is that we cannot control for a lot of factors. Like in regression analysis, we can have control variables, but if we want to control the impact of certain variables in portfolio analysis, we can do that, but there are certain limitations to the number of variables that we can use as control variables. Now, there are two types of portfolios. One is called univariate portfolio, and the second one is called bivariate portfolios. Now, first we would like to discuss the univariate portfolio. Now, what univariate portfolio is, as the name suggests, we just make portfolio based on a single variable. So let's say this is our example data set. Over here we have certain firms. We have around 11 firms, and we have just taken the data for 2020. Now it doesn't mean that you can apply this portfolio, univariate portfolio analysis on just 1 year, but for the sake of understanding, for the sake of simplicity, what we would do is we would understand all these techniques on single year, and once we have understood these portfolio construction on the basis of single year, we can replicate that same process on other years. And we have over here market capitalization that is used to represent the size of the firm. Now market cap is equal to number of shares into the share price. So what we do in univariate portfolio is that first we sort all the firms on the basis of the variable of interest. So in this case, we would sort the firm on the basis of market capitalization or size of the firm. So let's sort them in descending order, right? We have the bigger firm are at the top and the smaller firm at the end of the list. What we do next is we divide these stocks into two different portfolios, because this specific portfolio contains the big stocks, the big firms. Let's call them big stock portfolio, and the second portfolio contains the stocks that are relatively smaller. Let's call them small stock portfolio. Now in this specific case, what I did is I use a breaking point or a cutoff point. In this specific case, I have used median. So if we take the median of all this data, it turns out to be 8.05. So all the stocks that are less than that median point should become small stocks, and any stocks that are greater than that median point should become big stock. Now it is not necessary to just use median to divide these stocks into different portfolios. We could have used any other method. We could have used mean, we could have used standard deviation, or we could have used percentile. Secondly, it is not necessary to just divide them into two parts, two portfolios. We can have as many portfolios as we can. In this case, we sorted them in descending order, but it is not necessary. We can also sort them in ascending order. The answer would be the same. We would still have the same stocks in the small portfolio. We would still have the same stocks in the big portfolio. So I have combined the data back just to have an understanding. I have created a column, and within that column, I have the word big stock and small stock to represent whether that specific stock is a big or a small stock. Once we have formed the portfolios, the next step is to merge the monthly stock data or daily stock data or whatever frequency of data that we want to use. The portfolios are constructed yearly or monthly or at whatever frequency you want. In this specific case, we are going to construct portfolios yearly, and then we would have the monthly data. So if you look at this specific firm, that is 10010, we have their data for 2020. For each month, we have their stock returns, right? In each of these months, it still remains as a big stock, because what we did is that we categorized this firm into big stock and small stock in a specific year. And when we merge that with the monthly data, the categorization would remain same. So the idea is that we can construct portfolio yearly, and then we can merge that with a monthly returns data. So once we have monthly stock return data, the next thing is that we need to calculate the portfolio returns. We have the stock return, we need to convert these stock returns into portfolio returns. So what we do is we take for each month, we take the cross-sectional data, right? So we have all the firms that are within the big stock. So for each month, what we do is we take the average of these returns. So that turns out to be 32.2 for the month of January for the big stocks. We do the same for small stocks. And so what we do is we calculate portfolio return for each time period. This is how our data would look like. We have big stocks, we have this time series data, and for each month we have the portfolio returns. The same goes for the small stock. We have the time series data. For each month we have the portfolio returns. So now we have the portfolio return for the big firms and the small, or we can say the portfolio return for the big stocks and the small stocks. What we do is we can take the average of all these returns, and that would give us a single number. So let's just say what this number represents is that it is the average return for big stocks, and this is the average return for small stocks. So from this we can conclude that small stocks earns higher return as compared to big stocks. Now in this case we just had two portfolios, that is small stocks and big stock, and we can see that small stocks earns higher return as compared to big stocks. But the pattern is not quite clear in this case. To be more clear about the pattern, what we could have done is we could have created more number of portfolios. So we would have small stocks, and from small stocks till big stocks we would have say 8 more portfolios within this paradigm. And so the advantage of the more number of portfolios would have been that we could have seen a clear pattern, that whether the pattern is increases as the size of the portfolio increases. If that was the case, then we would have been more confident on our analysis. Now the downside of having more number of portfolios is that each portfolio would have less number of stocks. So we'd have to make a balance between the number of portfolios that we have and the number of portfolio stocks we have in each portfolio. So let's move to bivariate portfolio analysis. And in bivariate portfolio analysis, we have further two types. One is called bivariate independent portfolio or bivariate independent sort, and then we have bivariate dependent sort. Now, what bivariate would mean is that we use more than, we use two variables to sort stocks into portfolios. So portfolios would be constructed on the basis of two portfolios, two variables. Let's just say we constructed a portfolio on the basis of size and book to equity market, or we constructed a portfolio on the basis of size and beta. Now let's first start with the bivariate independent sort. In the bivariate independent sort, we form the portfolio on the basis of first variable, and then we form the portfolio on the basis of second variable. But the idea is that the breaking point of both these variables, or while sorting these variables, is calculated independent of the another sort, and that's why it is called independent sort. The order of the sorting therefore doesn't matter whether you first sort in on the variable x1 and then sort it on variable x2, or whether you do it the other way around, that is first sort on x2 and then on x1. So let's move to the same example that we previously had. We had different firms. We had the data for year 2000, and then we had the market capitalization, which represents the size of the stock. We would sort them in descending order and divide these stocks into different portfolios, that is big stocks and small stocks, on the basis of certain breaking point. Now what happens next is that let's have this beta of the stock that represent the systematic risk of that stock. Now what we do is, now once we have form this big and small portfolio, we would, because this is a bivariate portfolio, we would have a second variable that we would use to sort stocks into portfolios. Now next what we do is we sort the stocks on the basis of the second variable, which is the beta in this case. Let's sort them into descending order. So at the top we have the high beta stocks, and at the bottom we have the low beta stocks. Now, when we are sorting these stocks on the basis of beta, we are sorting them irrespective of the size or the first variable, or irrespective of the first sort variable. So whether it is a small stock or a big stock, we have just sorted them on the basis of beta. And we would divide these stocks into high beta and low beta on using certain breaking point. Again, that can be median, mean, or percentile, or any other method that we can use. In this case, we would use median. So we have a median of 1.62. So all these stocks that are less than 1.62 would become low beta stocks, and all these stocks that are higher than 1.62 would become the high beta stocks. Now let's create a column where we would have high beta and low beta stocks. Now, how we would calculate the portfolio return and what specifically portfolio means in this specific case. So if we look at this specific stock, this is a small stock, but a high beta stock. So we would assign a specific portfolios to these stocks. These all stocks, these three stocks are big stock, and at the same time, they are high beta stocks. Let's call them high beta, big size portfolios. I've used the alphabet HB to represent high beta and big size portfolio. So H stands for high and B stands for big. We also have small stocks, but high beta, so that is HS. Then we have low beta big size stock and low beta small size stock. So because we had two sort variables and we had divided them equally into two portfolios on the basis of median, so that is 2 into 2 for portfolios. Next, what we do is we have formed these portfolios yearly, and as we did in the univariate analysis, we would merge the monthly stock return with this yearly sorting variables or the yearly sorted data. Okay, the next step is to calculate the portfolio return for each time period. So I would skip that part where, as we discussed in the univariate analysis, we already know how to merge them and how to calculate the average return. So we have this portfolios and we have their portfolio return rather than the stock return using the same method that we discussed in the univariate analysis. So we have over here, because of the space limitation, I have just given the 3 months data, but obviously you would have many more months, and obviously it just won't be 2020, it would be many more years. So we have these portfolio returns, and what we do is we take the average of these portfolio returns, and so this 21 represents the average portfolio return that a high beta and big size portfolio would earn. To make a pattern out of it, let's convert that into a table. So if we look at this table, I have just converted these returns into this tabular format so we can easily analyze it. We have over here beta, that is, we have low beta and high beta, and then we have small size and big size portfolio. And at the intersection of these two variables, we have a portfolio. So what we can see is that as we move from low beta to high beta, the return increases, right? So the difference is +9. That means high beta stocks earn higher return as compared to low beta stock. And this similar is the pattern in the big stocks, right? So the low beta stocks earn 15% and the high beta stocks earn 21%. These are obviously the hypothetical results, so do not compare them with any theory or theoretical perspective. We can also see a pattern over here that as we move from big to small stocks, we earn a higher return. Okay, so let's move to bivariate dependent sort, and we would use the same data. We would sort them into descending order, then we would divide them into big and small portfolio based on, let's say, median. We would bring in our second sort variable, which is beta. The point that is different in the independent sort and the dependent sort, that is the bivariate independent sort and the bivariate dependent sort, is that in the bivariate independent sort, we would sort the stocks on the basis of beta irrespective of the first sort variable. But in the bivariate dependent sort, what we would do is we would take the small size stocks, right? Let's say big size stocks, and we would sort them into big portfolios. We'd sort them on the basis of beta. Similarly, we would go for the small stock. We would sort them on the basis of beta. So we are sorting the stocks on the basis of beta for each of the size separately, right? So that means that the first sort does matter. And let's divide stocks, these big stocks, on the basis of beta using median point. So we have calculated the median for just these values based on the basis of this median, we would divide these firms into low beta and high beta stocks. So any stock that is greater than 1.6, that would become high beta stocks, and the rest would become low beta stocks. So over here we have high beta stocks, and then we have low beta stocks, and obviously these are high beta big size portfolio. That's why we have HB, and these are low beta big size portfolio. The same would go for the small stocks. We would divide them on the basis of median being lower than and higher than median. So these are the portfolio names that we have: the high beta big size stocks, the low beta big size stock, the high beta small size stock, and the low beta small size stock. I have created a column over here that represents the name of these portfolios, and we would calculate the stock return, the portfolio return in the similar way as we discussed in the bivariate independent sort. So let's move to the second section, which is breaking points. And now, what is breaking point? It is the value that is used to group stocks or firms into different portfolios. So we can use median, mean, standard deviation, kurtosis, skewness, or percentile. So that depends on the research design that you are pursuing. So in previous case, we had been using median of 8.2 to divide stocks into big and small stock. But what if we had exactly same number as we had one of the market capitalization in our data? What we would do? Would this specific firm become a big stock, or would it become a small stock? When that case happens, this specific stock would be assigned to both the big and the small portfolio. Remember, anything above this median would be considered big, anything below this median would be considered small, but anything equal to this median value would be represented by both these portfolios. Now, this would rarely happen, especially if you have a continuous variable where the values for different firms are not quite similar. And secondly, when you have a large sample size where you have a lot of firms in your data. So this is a rare case that would happen. Now, it is not necessary to divide stocks on just basis of median. We can use percentile. So let's just say we calculate the 30th percentile, which happens to be 5.4. So any stocks, all those stocks that are less than 5.4 would become small stocks. If we were to divide them into 3 portfolios, let's just say we use the 70th percentile. So all the stocks that are greater than 70th percentile, which in this case is 11, would become big stocks. And all the remaining stocks would become the median size stocks. What I mean to say is that we can divide it into multiple number of stocks, and we can use percentile, and normally percentile is used in asset pricing domain. But do remember that the number of breakpoints that we would have would be one less than the number of portfolio that we are going to construct. So in this case, we are going to construct 3 portfolios, but we only have 2 breaking points. Okay, so let's move forward. Now do remember that the number of portfolio and the number of breaking point will be same for all time periods, right? So if we are using 2020's data, we would have 3 portfolios and we would have the 30th and 70th percentile. This would remain same for 2021, etc. We would still have 3 portfolios and we would still use 70th and 30th percentile, but obviously the value would change, right? So in 2021, we would have a different value rather than 11. So the value of the, for example, we have this over here, 2021, still we have 3 portfolios, we still have 70th and 30th percentile, but the breaking point is now different. The breaking point can also be calculated on subset of the data and then applied on the superset or subset or totally another set of data. For example, over here we have stocks from NYSE, New York Stock Exchange, and Amex, American Stock Exchange. Now in asset pricing models, what they usually do is that they do not include, they just calculate the breaking points on the basis of NYSE and then apply that breaking points to whole data. So in this case, we would just calculate the breaking point on the stocks that are listed at NYSE exchange. That happens to be 9.1. Now what we do is we take all these stocks, including the MX, right? and take that 9.1 median that we had calculated just for NYSE and apply that median to all the data. So the breaking point can be calculated on subset of the data and applied to all the data. Now, the reason for doing this in this specific case is that the NYSE stocks are usually large size stocks and the MX and NASDAQs are usually small cap stocks. Now, if we take all the samples and divide them into portfolios based on, let's just say, certain method, certain percentile, what that method would do is just literally separate the NYSE from MX and NASDAQ, because MS and NASDAQ are small stocks. They would end up all in the small stock portfolio and all NYSE would end up to be in big stock portfolio. For this reason, we use the NYSE, only NYSE as the way of calculating the breaking point. Now, this is what we have already discussed. The higher the number of portfolios we have, the lesser would be the stocks in each portfolio. And then there is a trade-off between the number of portfolios we have and the number of entities we would have in each portfolio. Let's move to how do we calculate equal weighted versus value weighted portfolio return. When we discussed the univariate analysis, we calculated this average return of the portfolio. Now, that was a equal weighted portfolio where we assign equal weight to each stock in our portfolio, right? What if we, the actual method should be that we should use value weighted return. The more accurate method is to use value weighted return. And how do we use value weighted return is that we sum up all the market capitalization in, let's just say, big stocks that turn out to be 88 million. Similar goes to small stocks. This is 22 million. Next, what we would do is we would calculate the respective weight of each stock in the portfolio. So we would divide this 25, this market cap of this first stock, on the total weight of the portfolio, total market cap of the portfolio. And then we would take the stock returns and multiply that with these weights. Once we do that, we would have weighted stock returns. And if we take the sum of, remember, we would have to take the sum rather than average. We would take sum of these stock returns, then we would have the weighted portfolio returns. Let's move to the last section of this video. That is, how do we calculate the SMB and HML? These are the two factors that are used in the Fama and French. The first factor is obviously the market factor, but this is what we have already understood in the CAPM. We already know what market factor is and how to calculate the beta or the systematic risk. Now, there's two factors that are new as compared to CAPM is SMB and HML. Let's discuss SMB. SMB stands for small minus big. That is, we take the returns of small portfolio, we deduct the returns of big portfolio. That is where the word SMB comes from. Now, this represents the size factor. So what we say is that on average, small stocks earn higher return as compared to big stock. That is what the size factor or the size effect is. Generally, it had been seen that small stocks or small portfolio earns, the portfolio with small stocks earns higher return as compared to big portfolio. The second factor is the HML factor, which stands for high minus low, and what high and what low. So what we do is we create a portfolio on the basis of book to market ratio. So we deduct the returns of high book to market portfolio. So we deduct the returns of low book to market portfolio from high book to market portfolio, and that is what is called HML, high minus low. This is what we call value factor, and on average it had been seen that value stocks, which is the high book to market stocks, earn higher return as compared to the growth stocks, which is the low book to market stocks. Now, what Fama and French do is they create bivariate dependent sort based on the market cap, which for size, and book to market for value factor. And we are going to look into how we are going to construct these portfolios. Now, this is an excerpt from a Fama and French paper. What they say is that in June of each year, all NYSE stocks on CRSP are sorted by size, that is market equity, to determine the breaking point. Now the thing to understand over here is that, as we discussed in the breaking point sections, is that we are just going to calculate the break point using NYC stock and apply that on all the stocks, that is on NASDAQ and on MX. The second thing is that portfolio construction would specifically on the basis of size would be done in June. So what we do is we take the market capitalization from June of each year, right? Not December, not any other month. We take the market cap for June of each year. We sort them in descending order on the basis of market capitalization, and we divide them into two portfolio on the basis of median. So in this case, it happens to be 9.1. So all the firms that have lower market capitalization would become small stocks, and firms with higher capitalization would become big stocks. Now, before we understand how do we sort stocks on the basis of book to market ratio, we would first have to understand how book to market ratio is actually calculated. Now for that, let's look at this sentence from the Fama and French paper. What it says is that book to market equity is the book common equity for the fiscal year ending in the calendar year T-1 divided by market equity at the end of December T-1. So we have to understand, it's quite a complex sentence. To understand this, we have this example data set where we have a single firm, which is 10010, and we have their monthly data. Now we have a column called calendar year, and then we have this fiscal year column. Let's say this firm's fiscal year ends in June. So from Jan till June 2022, it would be fiscal year 2019, whereas the calendar year would be 2020. Similarly, from July till December of 2020, it would be calendar and fiscal year 2020, and so on and so forth. Then we have market capitalization and book equity. What it says is that we take the book equity for the fiscal year ending in calendar year T-1. Let's just say we take the fiscal year ending. This firm's fiscal year ends in June. Now, to make it easy for us, I have color coded this calendar year and fiscal year. Now, what it says is that when the fiscal year ends in, the book equity is taken for the fiscal year ending in calendar year T. So if we look at this firm, its fiscal year ends in June. So we would take the June's book equity divided by the market equity at the end of December T-1. So this firm's market equity from December, we would divide these numbers. Now, to ensure that the accounting variables are known before the returns they are used to explain, we match the accounting data for all fiscal year ending in calendar year T-1 with the returns for July of year T to June of year T+1. So what this says is that this is the year T-1. What we do is we shouldn't form the portfolios in January of 2021. Rather, we should wait at least 6 months, right? So that we can make sure that this information is available to the investor, and we should form portfolios in July, and then from July till June of next year, that is T+1. So this 2020 becomes T, and 21 becomes T, 2020 becomes T-1, 22 becomes T+1. So from July of T till June of T+1, this is the portfolio holding period, and this is where we would take these values and divide them, and we would form the portfolios. Now, once we understand how book to market ratio is calculated, let's get back to the portfolio that we had already created. That is the big stock and the small stock. What we do is we do the bivariate dependent sorting. That is, for each of these portfolios, we are going to do the sorting separately. But this time, instead of median, we are going to use the percentile. So we are going to use 30th and 70th percentile on the basis of book to market ratio. So anything lower than 30th percentile would become low book to market ratio portfolio. Anything higher than 70th percentile would become the high book to market ratio, and anything within would become the median percentile portfolio. So let's take book to market ratio, sort them and divide them on the basis of 30th percentile separately, because this is bivariate dependent sorting. So we would have the low book to market ratio, we would have 70th percentile, we would have high book to market ratio, and the rest would become median. We would do that in the same manner for the small stocks. Then we would have this BH, BL, BM, SH portfolio, SL and SM. That's so we have 2 portfolios on the basis of size and 3 portfolios on the basis of a book to market ratio. So we have 2 into 3, 6 portfolios. Next, we are going to calculate the value weighted returns of the portfolio. And we also already understand how to calculate value weighted return of the portfolio. So what I have only done is that I have converted these portfolios, calculated their portfolio returns and converted them into a wide format so it is easy to understand. So we have SL, SM, SH. These are small portfolio. This is small low book to market ratio. This is small medium book to market ratio. This is small high book to market ratio. This is BL, which is big low book to market ratio, big medium book to market ratio, and then we have big high to book to market ratio. We are going to calculate the SMB factor. For that, we take the average of SL, SM, SH. So we have average of small portfolios because these are all small. So I'm calling this column as average small. Then we have average big of average of BL, BM and BH. Next, we are going to deduct the average of big portfolios minus the average of small portfolios. So we have the SME factor. Similarly, we are going to calculate the HML factor, which would be the average of SH and BH. These are the high book to market portfolios, right? High book to market small and high book to market big portfolio minus the low book to market portfolios. So we would have average high. This would be the average of this SH and BH, and we have average low, which would be the average of SL and BL, and we would calculate the HML, which would be the high minus low portfolio. So I hope you have understood how to calculate the SMB and HML factor. In our next video, we are going to look into the strata code that we can use to replicate the Fama and French portfolio construction procedure. We would use this exact understanding to replicate it, and we would see at the end of that video, we would see how close our replication is. So stay tuned to this channel, do subscribe and do hit the bell icon.